Okay, welcome to a walkthrough video of the LibreRISC-V IEEE floating point unit. What I'm going to do here is I'm going to demonstrate some of the use of nmigen, and which is a Python-based HDL that backends to Yosis and uses Yosis to generate the intermediary language or the verilog as required. Now, here is the original adder.v code which we copied. This is John Dawson's original code, and you can see that it uses global variables here, which and it's a state machine, so there's some states defined above: get A here, etc. Those moves on to get, once it's done get A, it will move on to get B, etc. And by comparison, what I've decided to do in the Python code equivalent, in the nmigen version, is to create classes and modules. So all of this code here, where the information is, this is one function and it's large. This one, by contrast, actually fits almost on a single page, and if, as you can see, there is a parameter in the Python module which switches it between single cycle and multi-cycle mode. If that was not there and was properly simplified like these, this function would fit onto one page. So you can see here that what we've done is created an add stage module and passed in its inputs from the previous module. So add 0 outputs to something called add0.outTotal and outz. Its inputs it's set up with the input from the thing. It is not storing in global variables, so this can be converted to much more to a pipeline. If I show you the GTK wave, you can see here M.8, 9 and 10 and 11 are in fact now, after 2 weeks of conversion, you can see that it's going in a staged single cycle thing. FSM underscore state, I can just do, what do we do to get that to move up without going on thing there. FSM escape here, this line here. You can see it moving in a single cycle. The one thing I wanted to particularly do was to show some of the conversion that needs to be done. I've got to where are we? A line single. Right. Yes, this is the module. I'm not totally happy with the way that modules are set up in nmigen. You need to declare you can't use them as you can't declare the inputs and outputs as parameters. It's implicitly worked out from how they are used when you do the simulation or the compilation. It's quite smart but odd. So you pass in Python parameters into the initialization of the module, and you declare the members of the module and where they are used and added into the module. This is where the actual thing, it's equivalent to a verilog module. you have to kind of get used to that, and then you actually have to connect those with either combinatorial or synchronization, combo sync, and that's what this setup function is for. So you pass in the parameters and they're connected to these inputs and outputs of the module when you actually use it. So coming down here to where it is used, this is the class FP add line single is where we actually use this module. Here are the two outputs A and B. So basically what this does is equivalent to, let's go over to the line here. This is just the equivalent to in the original John Dawson's verilog. However, to do a proper comparison we'll need to compare with the multi version, when you'll see the multi. Right, here we go. So if A is greater than B, do the shift down, which is a single shift, and the shift down function is over here, and that returns the logic for doing the new exponent increased by 1, and the mantissa shifted down by 1 with the merging of these bit 1 and bit 0 as bit 0, and then concatenating with the remaining bits 2 upwards and a 0, and that gives you a shift down result. Those get stored in the output, not, as you can see here, in the global variable B. So these are quite subtle differences. Anyway, we for this particular design only works on a multi-cycle environment, which of course is not suitable for pipelining. So what we did with the single version was do a comparison of the difference between the exponents and do a multi-shift, shift down multi, shift down multi, which, oh yeah, here it is, shift down multi uses, well this is just a wrapper, where this class here is, multi-shift is just a wrapper around the shift operator, but it truncates the result to the length of the incoming operator. By default, nmigen will extend the result on a left shift. Now, it's as explained in one of the updates which we published on the Consequently website for the LibreScribe GPU. When doing the shift down, you need to merge the sticky bit. Alright, but when doing it in a multi-shift, which bits do you merge? You need to merge multiple of them, and you need to be dynamically decided. So what we decided to do, as you can see here, is a right shift of the mantissa here. You can see the cursor on this line. However, to work out which bits need to be merged, we take a series of ones, all ones of exactly the same length as the mantissa, right shift that down, but you have to, you can't shift down by more than the length of the mantissa, so that's what that's about, is to restrict the amount that it's shifted down by. Whilst you're shifting the mantissa down, you want the opposite number of bits, so it's the length of the width of the mantissa minus the amount that you're shifting down. That gives you the mask. Those are the bits that you want to determine whether any of them are set to 1. So you take that mask, and it with the mantissa, and use this .bool operator, and I'll show you that here. This is where are we? We want %3 def bool. Right, this is a Boolean operator from nmigen, which returns operator. That's for the simulation result when the abstraction is syntax tree. So that is what gets converted to through IOSIS or interpreted. It's a conversion of Boolean. So the important bit is this documentation we're looking at here. So the output value is a single bit. If any bits are set in the input, return a 1, otherwise return 0. And that's exactly what we want here. Right? So you specify as the input the difference that you want the mantissa to be shifted down by, which is used to calculate the mask, which you then, of the remaining bits in that masked out, if any of them are true, it gets merged in with bit 0 of the mantissa, and there's the concatenation. That's the sticky bits. I want W save that. Diff mix rename sticky bits variable. There we go. So single sticky bit concatenated with the rest of the result, which was the bits 1 and upwards, right shifted down, and zeros in the top bits. So there we have the equivalent in a single version, single cycle variant of the multi-cycle alignment. Now what you need to do in add, this is an add, what you need to do in adding is the mantissas, the exponent need to be the same magnitude, so you can align one, either A or B, but not both. That's very different from a multiply. A multiply, you do normalization on both of them, but for add, you want the exponents to be the same magnitude, and you shift the mantissas accordingly. Right now, let's do a conversion on that module to IOSIS intermediate representation, intermediate language. And here's a command I prepared earlier. Yeah, I haven't. History. Pipeline grep IL 50. Ha ha, very funny. Non-shift multi. Right. Haha, very funny. Comment that out, comment that out, comment that out. Test Python 3. Duh. Good. That works. Let's try that again. Good. Generated. Now let's have a look at the outputs. For load file, mark X, and what were we looking for? Go to marker C. We are looking for the module named align. Delete up to X, find module twice, delete all that align .il file, IOSIS, read ilang align.il, show. There we go. Alright, so now we have, excuse me, now we have this this module. So we've converted the Python nmigen into a graph representation of the actual hardware logic that's needed. Now, the reason why I wanted to do this is to show you that, okay, so I'm just going to navigate using cursor keys. Here is those 111s with those ones, that's the mask, alright, and here is the shifting right of the mask, alright, which and where's the shift right of the shift right? There it is. There is the shift right of the mantissa. Right. So here's M. There you can see there's M under that cursor, just that cursor there. So so the mantissa goes in to get shifted down bits 26 down to 1, so the bottom bit is skipped, so 20 bits 25 down to 0, 26 to 1 shifted down by 1 just as an input. The mux over here is the decision making as to the maximum of the it's limiting the difference that you're shifting down by to a maximum value. There's no point in shifting greater than the resolution of the mantissa, its bit width. So here, that where the cursor is now, that's bit 0 being ORed with the Boolean reduced shift right mask, alright, and it gets put into bit 0, whilst the shifted mantissa gets put into the higher bits, and that's your output. It's cool. But here's the problem, right? Let's go back to the verilog here. Can you see that these are mutually exclusive? So if signed AE greater than signed B, else if signed AE less than signed BE. When you're doing a single shift, that doesn't matter. With multi-shift, this is an extremely large logic block, so it's not really acceptable to do that. And you can see here what's happening is all of that logic is duplicated, right? So that's for A and that's for B, alright, so that's not really acceptable. So what we're going to do is we are going to put in a muxer temporary variable for the input and the output. So we're going to put we're only going to have one of these shift down multis. This is one of the disadvantages of having functions like this in Python, is that the things are hidden from you, which are just, well, it's a single line, it's a function, right? It's, it's not inefficient at all. Well, actually, yes it is. It's resulted in 2 identical copies of the hardware, which costs us gates. So we've got to deal with that. So that's what we're going to do here. Alright. So self out B. Let's it's an FP num thing, so we're going to take a copy of those. I'm literally doing this on the fly, okay, so it's a thing, so please bear with me. And we are going to let's call it imp and out. Temp in, temp out. Dum-dum. And we are going to t in, t T out, T in, T out. Okay, so now we have temporary modules, temporary temporary modules, which now fpnum base is just a Python class, which is a module in its own right, and this is why in here you end up with, where are you? Where is it? Dum, 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 dum. There. Right. So input A. So basically it's a trick to by using a module, even though there's nothing actually used in it, by using it a module, the M and E variables, which are names that are allocated by nmigen and bleed through to Yosis and consequently into the graphics output. This allows us to identify them by name, and we can associate them easily with the code, the actual code of where they were defined. fpnum base contains three variables, E, M, and S, for exponent, mantissa, and cycling. fpnum in is derived from fpnum base. Now, let's have a think. So, what we want is for we need a signal of the edif r. We need to copy the edif r as well, because that's going to be down to another signal. Dum dum. T diff. Okay. And what we want to do is to copy this. We're going to do unconditionally. T out, T diff, T in. Only you have one multi shifter because A and B align our roots. Only use one because A and B alignment exclusive, unlike when comments fit on one line. Right. Now, what we want is to copy in edif out B and in B into edif, tdef, timp andtout. So self to out of B dot eq brackets t out. So we're doing the equivalent of this tdiff dot eq and removing the use of the comma, and t in dot eq bracket self dot b. There we go. That was a trick. I'm not going to put in the case where it's 0 here. I'm just going to skip that and find B, place A, dot RA, replace A. That should do the trick. Soft dot width. Hang on. no, that was extra, wasn't it? It doesn't, does it? Width equals width. T imp. P FPNum right, %3 colon 383. Right, I've created a function called copy, not EQ. I'll show you that here. Def copy. Right, there it is. So basically it returns the combinatorial block for 3 copies from the input, for 3 EQ statements, remember, one which copies the sign, one which copies the exponent, and the other one the mantissa, and it is a member of the base class FPNum base here. So that's the derived FPNum in also derives from that. So now we should be working, and it's not. Let's have a look at, the main reason I did this was to show you the effect that it would have on the Yosis, who's we want to get rid of the duplicated text. W align.l read align show, and yes, it hasn't indeed. It's now a single use of the thing. It's not duplicated. Excellent. So here's the variable tdiff, temporary difference. That now goes into the muxer, align T in mantissa, not M as was previously exponent. There's the mask shift right, masking shift right with the ones, 1 1 1 1 ones, and there's the aligned mantissa, and we should have look, yeah, there we go, align T to out mantissa, which goes to either of output of B or the output A, depending on which is required. So that I'll fix that bug and make sure it actually works later. I just want to do a demonstration of how that's working, to remove what is clearly just an insidious and accidental use of a function, which looks, in software it's perfectly fine to do this, but in hardware it has obvious consequences that are only really show up when you look at these Yosis graph diagrams and see what the heck is really going on. So, thank you very much.